Hey guys, today we're going to talk about nitrogen. Nitrogen is one of the most important elements for life, for sustenance of life on the planet. Our planet has about 78% nitrogen, and we'll like about that. The most abundant, but also the most stubborn. It's a very, very strong bond. It's one of the nature's strongest bonds. It's a triple bond. The nitrogen atom is just bonded by another nitrogen atom. It's such a strong bond. The energy to break this bond is right about 940 something kilojoules per mole. That is the energy required to break this bond. And if you're not familiar with what kind of energy that is the energy of the core of the sun. Thousands and thousands of Kelvin is needed to break this nitrogen bond. So the next question is, why is it important to break that bond? Can't we just use nitrogen the way it is? The answer is no, we cannot. For life to actually sustain itself, it needs the nitrogen in the atomic form, so we can have amine compounds, which is needed for amino acids, and the plants, they set that up to make food, and nitrates. And those are the things that are extremely, extremely important for life to sustain itself. And we cannot do that if we are not able to break this bond. It's a battle. It's a battle for nitrogen. It is such a strong bond that we need the energy of the sun, 20,000 Kelvin. That is what is needed to break that bond. It's one of the strongest bonds. So how did we do that? One theory is that, hey, maybe, just maybe, we had giant aliens that took all the nitrogen from Earth all the way to the sun. Okay, that makes sense, right? We took all of the nitrogen in molecular form to the sun. Then they broke it down there and then built a ginormous invisible pipe. Built a big pipe all the way from sun to the Earth. All that beautiful molecular nitrogen broken down in the sun into atomic forms, and then we are able to use that atomic nitrogen to make life. Right? No, that's not how we did it. That's not any of this happened. So how did life eventually figure out to break this strong nitrogen bond? That is quite a bit of the mystery. But we have some clues as to how we did it. Well, first things, lightning strikes. The very first time we noticed nitric oxide, and nitric acids in our atmosphere and the soil was after the lightning strike. Okay, so the lightning core of the lightning is very, very strong. It is just the temperatures reach near the temperatures of the surface of the corona of the sun, thousands of kelvins. So when lightning strikes molecular nitrogen here, in presence of oxygen, then we have something that is formed that's called nitric oxide. Now, this is one of the first reactions plastered in almost all chemistry textbooks. Probably one of the first few reactions you learn right after you learn H2 plus O2 makes water. So right after that, you're probably going to be looking at carbon dioxide, carbon monoxide, you'll be looking at this. And why this is the most important part for sustenance of life, because this is the first time the energy of the lightning strike broke nitrogen down and turned that into nitric oxide. Now, the nitric oxide combines with the oxygen that's already in the air. And then it makes something we know as nitrogen dioxide. So that was the other step right after a lightning strike. We got nitrogen dioxide in our atmosphere. Then what happens? Our atmosphere has ozone. Part of what happens is If it's not raining, sometimes if it's a dry lightning, like a dry thunderstorm, this nitrogen dioxide is going to react with the ozone molecule that's present in the atmosphere as well to make nitrates. So that's one way. This is a bit of a rare occurrence, because before this would actually happen, if it's raining, usually lightning and thunderstorms, they occur together. So if it's raining, there's another thing that could happen. The nitrogen dioxide is going to react with the rainwater, and it's going to make nitric acid. And as far as I remember, I think part of it is also nitric oxide. So now if you balance the equation, let's see what we're going to need. We've got this. So to balance this simply would be this. Then, because there's 3 nitrogen, blah, 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 so you're probably be looking at two nitric acid molecules. So this might be balanced. So this was the next step. Now the nitric acid is basically what goes into the soil, and the plants are able to use those nitrates to generate food. There's another clue. As what happens is, if there's no lightning strikes, the molecular nitrogen also breaks down by bacteria called rhizobium. Now, the same thing, I mean, it's quite interesting to know that life itself knows how to break down nitrogen, and we don't. We don't know it the way life does it. Bacteria, the rhizobium that is sometimes present in the roots. These got root nodules. They've got these nodules right here, and they will have this bacteria that uses a compound called nitrogenase. That's a type of enzyme that is able to do this reaction and break down nitrogen and turn it into ammonia, which is what life needs, amino acids, to create life itself, to create food and this beautiful apple and orange. That's basically all a byproduct of nitrogen and hydrogen. So these bacteria, the rhizobium bacteria, they know how to break it down using this nitrogenase. So during the time of the World War, Fritz Haber, someone would call it, he was studying the behavior of these bacteria, because one of the biggest problems, well, he was trying to make a weapon for the Germans, but he was also studying this bacterial culture. And I'll tell you an interesting story. I was watching this show, Genius, on National Geographic. It's now also on Hulu, I think. So this is what actually inspired me to do this lecture on, because it just got some bells ringing. And Fritz Haber, he was trying to make a weapon. He wanted to make some sort of ammonium nitrate type weapon, and some gases. I'm not going to go into the details, but he was really studying these bacteria as to what they're doing, and he realized these nitrogenases, they are iron-based compounds. They have iron charged. Atomic iron present in there, some kind of a complex iron, sulfur, molybdenum, ruthenium. It's an extremely complex molecule. These acids, these enzymes, they have. But the bottom line is they have iron in the charged form, and that is why we need iron to live. So iron and nitrogen have some kind of chemistry that happens that we didn't quite understand, and I'll be honest with you, we still don't quite completely understand how this process works. But we were able to pin down that we need iron in its charged state, which is a Lewis acid. It's kind of like an acidic sort of atom. So then, after studying the nitrogenase and realizing that, hey, somehow tiny little bacteria are able to break the super strong nitrogen bond within minutes and at room temperature. So that kind of, the answer to that might be present in the structure of the nitrogen molecule as well. So the nitrogen molecule has a triple bond, right? The basics of it, if you do a Lewis dot structure, it will be something like this. but let's just think about it simplistic ways. The triple bond. Okay, well, if you remember nitrogen has an atomic number of 7, which means its first shell is 2, the second shell is 5. If you remember my last lecture, in the last lecture I tell you how these electrons in each shell are divided into suborbitals S and P. It's extremely important. So the second shell of the nitrogen atom, well, first is going to be 2 electrons. Second shell has 5 electrons. Okay, so it likely has 2 electrons that are paired and 3 that are not paired because of 2s2 and 2p3. Okay, so if you're not familiar with it, go back and watch my atomic orbital lecture, and it will be clear. And I recommend, before you even take any kind of dive into chemistry, it's extremely important to understand the atoms. Without that, your chemistry is just going to be gone. You're not going to understand a thing. So the 2p orbital has 3 electrons. Okay, so if you remember, the s orbital spin up down, and then the p orbital. There are 3 orbitals on the x, y, z axis. We call them px, py, pz. Each of them has an electron. That's the status of the nitrogen atom. Now, when this nitrogen is formed, it is going to bind these 3 electrons with the second nitrogen atom, whereas the electrons going in the other spin, and they're going to combine together to form a stable structure. So now we know that this is spherical shape. This is a 3-dimensional geometric XYZ coordinate system. So what happens there? How is actually nitrogen bonded that way? That the quantum physics of that is what gives us the answer. So now, if you remember that the p orbitals, they are XYZ planes. So this is X, Z, and Y. Okay. So let's assume that the first nitrogen atom has a p orbital that is going this way. Okay, that's a p orbital. Then a orbital pointing down on the negative z axis. Then these are half-filled orbitals. Okay, so one on the x-axis. Okay. So there is an empty space that's here. Okay. That is what the atom needs to go stable. So what it's going to do, this is the first nitrogen atom. The second one is basically going to find an atom that is a flipped upside down shape of the same atom. So let's make that the opposite spin. Okay, because they need electrons with the opposite spin. So it's going to find an electron that is from another nitrogen going the other way to make a bonding. Okay, so it's the same thing. It's going to be XYZ. So this one is upside down. So this is the one on the y-axis, and this is the one on the x-axis. Okay. See. So those 2 nitrogen atoms, they're going to be binding upside down, so these orbitals will eventually going to collapse into each other, forming one bond that is on the vertical z-axis and 2 parallel bonds that are going to connect this way. Sort of X with X and Y with Y, kind of like a parallel bonding. So now these opposite spins, this will be the opposite spins, make sure I make the opposite spin right here. So going down into the structure of the nitrogen, it makes a triple bond because they both need these orbitals filled. So these little opposite spins, it's going to find this and flip it, rotate it, so it makes a nice little compact structure. So now this bond, the one that's dangling upside down like this is called a sigma bond. If you're familiar, if you've taken some basic chemistry bond structures, they will tell you that this kind of bonding that happens is a sigma bond. And this kind of bonding is called a pi bond. So if you were to go by molecular geometry, these are going to be pi bonds, and there's going to be sigma bonds. Sigma bond is a stronger bond. Pi bonds are a weaker bond. So the pi bonds for the nitrogen are the weakest link. They're the weakest link in the structure. So to break nitrogen, we can't just attack right at the center. This is the battle. Like, this is the battle for nitrogen. We can't just attack right at the center of the sigma bond to break it apart. We have to slowly peel these pi bonds off. Okay, so to break that, it's actually quite easy. It's almost like electrostatic mechanics, where you're just twisting it on the axis just slightly, because they're just nicely lined up parallel. But if you break the angular momentum going the other way, it will break the dipole moment. It will break the bond that exists between those two pi bonds. It's easier to break. So how do we break that bond? So that's where these bacteria gave an idea, because we use iron, and charged iron, maybe in some way that the iron can slowly attract the electrons away from their axis, the way they're aligned. Eventually they're going to snap off. And that's exactly what Habers did, and got a Nobel Prize for it. And we're going to go into the next equation that is also plastered on the chemistry textbook. So high school chemistry all the way up to college, just plastered. We're trying to crack this equation ever since the day of chemistry. So ever since we started understanding any sort of chemistry, we've been trying to crack the mystery of nitrogen, the battle for nitrogen. How do we break it and use it for fuel, fertilizer? I mean, nitrogen is used for everything. We make fertilizers, we make amino supplements, we get medicines, we get all sorts of things. So anyway, this is the internal structure of nitrogen, a sigma and two pi bonds. And we need to slowly break these bonds to be able to use the nitrogen in some kind of a useful form. So what happens here? As we talked about the Habers process, the Habers process is practically the same thing, nitrogen, and the nitrogen reacts with hydrogen to make ammonia. So that is kind of like the basics of how these bacteria are working. They're trying to break down this nitrogen into ammonia. Let's balance this equation. It's going to be something like 2NH3. And it releases energy. It's an exothermic reaction. It's going to have some kind of energy release that in the order of, I think, something around 92 kilojoules per mole, something around that. So we need to get here somehow. Another basic equation. Looks very simple, but the chemistry involved in that is just so far complex that we're still trying to figure out. So what did Habers do? Habers said, hey, if the bacteria, they're using some kind of iron compound, I should be able to use it too. So what he did, he just took wustite or magnetite. It's an iron ore that has charged irons, that has a whole bunch of complex that has all kinds of family of charged iron. So is iron oxide combined in different forms. So it's sort of acidic in nature. It's a Lewis acid. So he said, I'm just going to take a big giant slab of iron. Okay, I'm going to take this iron. Now iron, they layered it with iron oxide, a whole bunch of porous material. So it sort of acted like a trap. Okay, like little holes here where nitrogen is just going to get stuck. Nitrogen incident coming down on this iron trap. This is an iron trap. Now, this does need quite a bit of temperature. I think it needs about 200 degrees, by 400 degrees, and maybe a pressure of 200 atmosphere. That's like 200 times the pressure of our atmosphere. It's huge. It's really, really, really strong. So then we need like something around the order of 500 degrees Celsius. So something like this. So it's really hot, and there's an iron surface with charged irons. Okay, and then it also has something of the sort of potassium hydroxide that sort of acts like a Lewis base. If you're not familiar with acids and bases, I might talk about it later, but just for now, just pretend that you know about the Lewis acid and Lewis base. So What this is doing is that the Lewis acid, iron acting like a Lewis acid, tends to attract electrons to itself. So it's hungry for electrons. The bottom line of adding the potassium hydroxide is to make the iron even more hungrier. So the potassium hydroxide base is going to be acting like an electron donor. So think of this surface is now charged with a whole bunch of electrons. And it's got iron sort of sitting there waiting to just catch nitrogen anytime it lands in there. So this process is called adsorption, not absorption, adsorption. If you've taken chemistry before, you'll know the difference, but the difference between adsorption and absorption is that in absorption, it's like sugar dissolves in water and completely dissolves, meaning the molecules kind of fit snug between each other and they just sort of dissolve. Okay, that is called absorption. In adsorption, this happens only at the surface. There's surface, there's pores. So the nitrogen is acting with solid iron, charged iron, and it's dissolving in it on the surface. That's called adsorption. Now, why we call it an adsorption is because it's not a complete dissolve. It is kind of like half stuck and half stuck beneath. So if I put a microscope here and just see what is happening here, what is the iron doing? So it's kind of like a triangulation. So you've got iron here, charged iron. Okay. And that's iron. So 3 iron atoms, they sort of form a trap armed with electrons on each side coming from the Lewis acid-base reaction of potassium hydroxide. But you don't need to know that in that much detail, but pretend that the iron surface is porous. It's got little microscopic holes in it, and the nitrogen is going to get stuck in there. So the space between these 3 iron atoms is enough to hang on to a nitrogen molecule. Okay? So when a nitrogen molecule gets stuck between the 3 iron atoms, the triple bond of nitrogen, there's iron here, there's iron here, there's iron here, okay? So it's this strength here gets put under a lot of electrostatic pressure, because iron is positively charged, which means it's going to start attracting the s electrons from the nitrogen s orbital. So, and then this thing here is applying torsion. It's applying a dipole moment that is trying to break the parallel pi bond. So these two iron atoms, they're trying to break the pi bonds. And this thing is just charged, and the moment this bond starts to weaken up, it's going to combine with the nitrogen and form a surface compound that is known as iron pernitride. So this thing right here was a secret to how the bacterias and how Haber use that to break down nitrogen. So this iron pernitride, it's kind of a newer compound. If you read chemistry right around early 2000s, you may not even be familiar with this iron compound, but this one is what gives the answer to how iron breaks down nitrogen into ammonia. So we'll keep going further. So the pi bonds are under a lot of pressure from this. It's a battle. The iron atoms, they're putting a lot of pressure on the nitrogen pi bonds, trying to break one of those bonds, So we're very close. We're very close to just breaking this. So the equation would be, now that we understand that the iron has trapped nitrogen as a molecule and is trying to put a lot of pressure on nitrogen. So what happens here? These bonds are starting to become weak. Okay, they're becoming weak. And because of potassium, this charged iron here is also putting electrostatic force on these 2 electrons in the s orbital of nitrogen. So this is the structure of FeN2. So once that's formed, these bonds slowly try to break. Now remember, we're putting a lot of protons into the mix. There's hydrogen coming from methane. That's a part of it. Is a lot of the hydrogen is still in the play here. A lot of it gets excited and it wants to combine with anything that's available. So we have to remember that hydrogen is coming into the same equation. Now iron is acting like a catalyst. A catalyst meaning it doesn't really take part in this equation. It just acts as a catalyst, a surface catalyst in this part, in presence of potassium. Potassium, that's a promoter. So it's got a promoter, which is what's helping put more pressure on the electrons, and it's donating electrons to the Lewis acid iron to make it more unstable. So then iron eventually breaks the bond, the pressure coming from the side atoms, the polar, the pi bonds. The pi bonds, this is the sigma bond that is not broken yet, but it's under electrostatic force, so it's attached. It's linked on the surface. It's not a complete bond yet. It's highly unstable. So then what happens? This triple bond starts to weaken, and eventually one of the bonds breaks. It becomes so weak, and there's hydrogen eager to just accept anything that's going to come its way. And that's why I call this a battle for nitrogen. It's very strategic. Everything is happening in a strategic fashion. So then hydrogen say, hey, one of the bond has broken up. I'm going to attach there. So then we've got that. Then there's more forces happening once this breaks. The weakest link eventually breaks. And then when the weakest link breaks, then all the other bonds start to fall apart, attached to hydrogen atoms. So something like this. So once the bonds start to break, hydrogen starts attaching to the compound. And eventually, this is so stable because now the bond energy, the bond affinity for the amine bonds is stronger than anything else. So it will start to pull away from the iron and it will start making ammonia. Like this bond becomes further weak. So then you've got iron just sitting there hanging with one amine right here in H2. And then this bond eventually breaks and pops off into ammonia. And then eventually same fate happens because now it's got an empty place where an electron can go, and then boom, this eventually breaks off, leaving iron right where it was, and you've got a release of two ammonia compounds, this and this. So that's kind of how this whole process plays out. So like I said, this process is called adsorption and cleaving. What we're doing here, this process is called the breaking of the triple bond into multiple steps using iron as a catalyst in the presence of a Lewis base. This is called cleaving. You're taking a cleaver to it. So kind of think of it like nitrogen getting stuck in between the iron atoms and getting pulled apart like mozzarella cheese. So it's almost like, hey, we're stretching the nitrogen like cheese. So the nitrogen bond slowly starts to weaken without even adding too much heat. We're just adding mechanical stress to it, adding electrostatic stress to it. So now, boom, nitrogen is broken and we have the release of ammonia. And Habers got a Nobel Prize for this, but it comes with a dark side. It comes with a dark side that the process of getting hydrogen is very carbon dependent. Methane, we're using fossil fuels. So to make millions and millions of tons of fertilizer every year, we're releasing a whole bunch of carbon dioxide into the air from methane. And that is not right for this. So part of what the latest quantum computers are researching is, can they make